Hello, everyone. Welcome to this edition of Tech Talk. Today, we're going to concentrate on the subscriber equipment, antenna and performance, and some gotchas when it comes to looking after your installation of your CPEs. As usual, if you have any questions or comments, feel free to send them to marketing@mbsiwave.com and let's enjoy the next 45 minutes or so together. So still on the topic of link budgets, this is just another facet of link budget. We want to talk about the CPE antennas. Typically, they're directional antennas. They have some sort of gain. They have usually quite a tight antenna pattern, although in the case of indoor Omni devices, that's not the case. But we're going to talk about outdoor devices here, since that's predominantly what we do here in the broadband wireless, fixed broadband wireless world. We're going to talk about some system behavior and the concept of best serving sector, and some maybe different definitions of interference than what you're used to, and what we can expect for performance out of all of this, just like we did with the base station antennas last month. Okay, so here's our little model of the link budget, and of course today we're going to be talking about the CPE device that's out here actually. And so and we're going to concentrate on a typical broadband OFDM system. We're not going to talk about Wi-Fi based systems, although the principles are still all the same, but specifically we're going to talk about performance in an OFDM based system. So I'm talking about, of course, Cambium's 450 system. I'm talking about any of the LTE systems out there, and as we move on in the future, more and more of them are going to be OFDMA based as we move into Wi-Fi 6, for example. All right, so a typical CPE antenna, this happens to be a 450B high gain antenna pattern that we see here. We have the horizontal pattern on the left here, and we have the vertical pattern on the right. Now this could easily what we can see here, of course, is that we have a main lobe. We have some side lobes that are associated with this antenna, and those are due, of course, be the physical construction of the antenna. We see that we have no electrical tilt in this antenna, and we have 19 dBi gain in typically in this antenna, although it might vary a little bit between frequency bands. 5 gigahertz typically has higher gain than 3 gigahertz because of the fact that the antenna itself is smaller, and so for an antenna of the same size, it will have more elements in it, and so it'll have higher gain. Principle: lower gain, wider beam width; higher gain, lower beam width. That's the principle. So the higher gain we go, the tighter that this main lobe is right here, and the tighter that this elevation beam width will be right there. So keep that in mind as we move forward here. All right. Each subscriber location has a sector that has the highest system gain when connected. Remember, the system gain is the gain difference between the transmit power of the sector itself and the receive sensitivity of the CPE in the downlink, and of course the opposite in the uplink. And we can calculate the downlink and uplink signal strength, RSSI, that we can expect from a particular distance, and simply by knowing what that distance is, we can calculate the free space loss. And so if we know the frequency, the distance, we can calculate what we would expect to see in a line of sight condition at a particular CPE location. It's not a big, it's not rocket science anymore for us. So Here in a typical case, we have transmit power maybe of 1 watt. We have an uplink transmit power maybe of 28, or maybe it's 23, something like that. The base station sector gain typically 15, 16, 17. The CPE antenna gain anywhere from 15 to 24, maybe something like that. And in this case, we're going to talk about, let's assume that we're at the 5 gigahertz band here. So in our first exercise here, we can calculate what the expected RSSI is of this particular link. So I'm not going to take too much time to run through the math here, because it's simply just a case of adding the gains and subtracting the losses, and we end up with at this typical. I would expect the RSSI at this CPE location to be around minus 40 dBm. So we have this this number 608 here is our target subscriber module, and we're going to take and we expect to have that kind of signal level in line of sight at that particular location. Now, if we calculate the system gain the other way, the expected RSSI at the base station, if we work it backwards into that, because we have 2 dB less transmit power out of the antenna, we would have 2 dB less RSSI at the base station. Goes to that's exactly what we'd expect. Now, I want to talk about automatic transmit power control in the uplink as we're going to go through this here. Let's make the assumption for our next little calculation here that the uplink automatic transmit power control has a target RSSI of minus 60 dBm in the base station. What would you adjust the power on the CPE to? All right, so the formula is a little bit different now. So we have an expected RSSI, we have a transmit power that we're looking for, we don't know what it is. So our formula, a little bit different, just arranged a little bit differently now. So I would expect that for us to receive a minus 60 dBm at the base station, we're going to turn the transmit power down from our maximum of 28 down to 10 dBm. Is the power that I would expect out of my customer premise equipment or my subscriber module. So why do manufacturers employ ATPC? There's a number of reasons, and I'm going to go over a few of them here. All right, so here's a map. Here's a close-up of our little sector here. We have, of course, our target, our subscriber module there, number 608. We have a number of other subscriber modules here. The blue would indicate that they're in coverage. Outside of that, then maybe not. So probably 199 is not in coverage at whatever height the CPE was modeled at here. So maybe you have to go a little bit higher, maybe something like that. But anyway, so there's the coverage area. The coverage area is our blue area. What's the difference between number 79, that's this one, number 608 that I pointed out here, and number 1923, which is right here? Let me erase my 199 here. All right, so what's the difference between those three? They're all, let's assume that they're all line of sight. That would mean that the only difference from each one of these, if the transmit power were the same on all of them, is that the RSSI would be higher here, a little less high here, and it would be lower here, right? So we have this just the RSSI is a function of range. So we have that's the difference. What does that do to the base station? All right, let's take a look at what OFDM really is, just for a second here. So the acronym OFDM stands for Orthogonal Frequency Division Multiplex. Orthogonal means that the carriers are beside each other. And so here in this graph in the upper left here, we have a case of an OFDM carrier. When they're generated in the transmitter, the carriers are all spaced equally, They all have relatively equal amplitude, and as the channel is transmitted, some of them are carrying the data for your subscriber, and some of them are pilots that the receiver at the other end, whether it's in the uplink or the downlink, uses to synchronize to that particular signal, so that the subscriber module knows where the location of each of these pilots are, and so then it knows that this is a pilot, and then these carriers contain data, and this is another pilot, and so this is what synchronization is in OFDM. The receiver knows exactly what the content of each of these carriers happens to be. All right, so OFDM has a high peak to average energy ratio across the channel. What does that mean? That means that because of the fact that we have energy in each of these carriers, and we have very little energy in between the carriers, that means that I have peaks of power in the channel in the frequency domain, and I have places in the frequency domain, like we show in the second graph here, that the channel power is much less. So when you look at it with a spectrum analyzer, you don't see this very nice OFDM signal unless the signal is very, very strong. Then you might be able to, with the right resolution bandwidth, you might be able to pick out where the OFDM carriers are. But typically, as it travels through free space and arrives at a receiving antenna, and you look at it with a spectrum analyzer, this is more likely what you're going to see. You're going to see some energy very high, some energy very low. Your average energy is going to be this green value here, the green axis here on the graph, and the peak power is going to be somewhere near the red. So you can see the difference between the peak and the average. So this is the peak to average ratio. The lower the peak ratio is, or closer to the average ratio, the easier a decoder, a receiver, has to decode the signal. In the case of OFDM, now we need to have quite a bit of signal to noise ratio in order to take and make sure that we can take the data out of this signal because of this peak to average noise ratio. This leads us to a number of things. We have in the challenges in the channel, twofold here. One is that we can have frequency selective fading. So that's what we kind of see going on here. The actual peak looks something like this, right? So the actual peak looks something like that. So what we have going on as the signal travels from the transmitter towards the receiver is that we have variations in these carriers as they travel through the air because of interaction between the carriers, because of interaction with free space itself, and just a number of anomalies that occur here. I'm not going to get into propagation in this. The point is that we have this business going on here. It's called frequency selective fading. That's the wider the channel, the higher the frequency selective fading is. That's why sometimes that when you're using an 80 megahertz channel and you reduce it to a 40 megahertz channel, the difference in performance, you'd expect it to be half. Sometimes it's not half. Same with going from a 40 to a 20 megahertz channel. And in fact, in a report that I like to read from a company called Prescene, which does bandwidth shaping devices, they have a very interesting view of the spectrum as we know it. The difference between 20 and 40 megahertz channels is not half the performance. It's more like 70 or 80% of the performance. So sometimes having a narrower channel has advantages in that this frequency selective fading is much lower. Also, we have a situation where this carrier and this carrier, for example, as they're traveling through this free space here, they can interfere with each other. So right here in this plot, of course, they're all you know, nicely sitting in the null of the second harmonic of each one of the carriers. The peak that we see here is primary. The peak that we see here is right there. So if this were the primary, this peak is the third harmonic. This peak would be the fifth harmonic of the carrier. So we have this this business here where the adjacent carriers are placed where the second harmonic would normally be, which is normally negative. So the third and fifth harmonic are values that add to the signal. The second harmonic and the fourth harmonic are values that take away from the signal. So what a great place to put the adjacent carrier beside it. So now in this business, as we have frequency selective fading going on, we can also have interference between these carriers going on. The receivers are sensitive to the difference in amplitude between these, because as I mentioned, remember I said that the closer the average rate, the peak ratio, the peak energy is to the average energy in the channel, the better the receiver is able to decode that signal. So in this particular case now, if I have one carrier that has a huge amplitude and one carrier that has a less amplitude, in that case, it could be that this third and fifth harmonic of these carriers actually affects this adjacent carrier beside it. That's called subcarrier self-interference or subcarrier interference, and it's a contributor. Multipath contributes to it, the frequency selective fading contributes to it, and design of the equipment and installation of the equipment contributes to this subcarrier self-interference. So in theory, demodulating the signal has its challenges, but if we're not careful with our installation or we're not careful with our implementation, we can make it even harder. All right. So let's look at some concepts here of the concept of signal to noise ratio. Now we've seen it before. I've presented this the plot of the QPSK to 30 or 256 QAM takes from 8 to 32 dB signal to noise ratio to be able to demodulate it. Each one of these carriers for the symbol period that it's on the air is going to be represented by one symbol, or maybe a group of symbols depending on how wide it is, but it's going to be at least one symbol. And this little chart that I've got here shows you how many symbols are represented by each of the different modulation levels. So the 256 or 64 QAM, that's called you'll see it called a modulation coding scheme, MCS. The reason it's called coding scheme is because the carriers, the symbols, I should say, in the carriers have some data, and they have some forward error correction. FEC, forward error correction. That's part of each symbol. So it might be 2 bits or 3 bits or 1 bit, depending on of the bits represented by the symbol that are actually forward error correction, and so the system can mathematically correct its errors in it when it knows what the forward error correction value is for each symbol. If the signal to noise ratio is not quite high enough, but it knows what the FEC is, it can take and mathematically make that judgment as to what the value in that symbol actually is. All right, so in our little OFDM diagram here, I've outlined pilots and I've outlined data. So this is a pilot, that's a data. So what we have here is we have the pilots. Pilots are typically BPSK, but they might be QPSK, but they're typically BPSK. And then the data are all these other modulation levels. So the pilots can be decoded quite easily. BPSK can be decoded all the way down to 3 or even close to 0 dB signal to noise ratio. We can't pass any traffic at that, of course, because it only represents 1 bit. So I would only be able to get on a 20 megahertz channel, I would only be able to get a few hundred kilobits of data across that channel at BPSK, but it would be very, very reliable. It's not enough data across the channel. So we modulate the subscriber data with some values that are of modulation that are much higher than that in order to pass the traffic that we need. Keep that in mind as we're going forward here. We need to have a certain amount of signal above the noise in order to take and decode this data. Now, if we had no automatic transmit power control, we would see that the signal level would vary wildly across our channel. So here's back to our another diagram of what a spectrum analyzer might see connected up to the receiver of that's receiving a signal from many CPE at the same time. So one of the tenets of OFDM, of course, let me just go back for a second, is that a group of carriers might come from one subscriber module. Another group of carriers might come from another subscriber module. So in theory, let's say that is sub 1, SM1, and this is from SM2, so on and so forth on our channel, if it were all theoretically could be. So in fact, the way that OFDM is transmitted, it depends on how much data the subscriber module has to transmit to the base station. So if it has a lot of data, then it takes up a lot of the channel in time. If it and frequency. If it has a little bit of data, then it takes up fewer subcarriers. So in this case, we've got essentially we've got 3 major transmitters here. We've got one subscriber module, perhaps another one there. So maybe we've got represent 3 subscriber modules in this plot. In here, we have no ATPC running. So all the subscriber modules are transmitting at the energy that they, whatever they're configured to. So let's assume that they're set to the maximum. Now, it is possible that this energy is high enough that I am causing right in here, I'm causing subcarrier interference in between the transmissions that we want here. So these might be very, very hard to decode. Let me get rid of this. These subcarriers here, there, and there are extremely difficult to decode for the receiver. With these subcarriers shouting as loud as they are, makes it hard for the receiver to figure out what these are. These actually bleed over to here. The higher this level, the more these bleed into the weaker subcarriers. So if this were a whole series of receivers or of transmission subscriber modules that we've got from in our example there, we had the 3, then it's possible that if there's a subscriber module in here, that he's having to retransmit, and same thing here and here, right? These could be bad enough off that they're dropping the modulation level, they're retransmitting, all sorts of terrible things are going on here on this channel that's wasting time and bandwidth, of course, in the channel. All right. So automatic transmit power control then has a very important function. It takes and it reduces the energy, the peak energy in these, so that no matter what, if it's a far as subscriber module or it's a near subscriber module, the receive level is going to be very close for all of them. So whether a very close CPE is transmitting or one quite far away is transmitting, the signal level of this is reduced by lowering the transmit power control. The signal level of the weaker signal is increased by the base station telling the subscriber module to turn up. So in this case, we have down here, we have up here, and down here. So that's what ATPC is doing. If we let this in a perfect world, this would function so that all CPE would end up arriving at the base station with exactly the same power level. Now, just out of curiosity, why do you suppose we do not have that problem in the downlink? Why do you suppose we can take and have just a single transmit power control on the base station in the downlink? I'll show you here. All right, so in our little graph here, we've got, if we're looking at this from the downlink perspective, we're transmitting all of our carriers at exactly the same level. In the scheduler now, my CPE might be only receiving, let me get rid of our little peak to average, might be only receiving subcarriers right there. And so if that's the case, you can see that those subcarriers are all pretty even. So there's probably not going to be any subcarrier interference here. All receivers also have something called automatic gain. Let me say that again. They all have a function in them called automatic gain. And so in this automatic gain control, what happens here is that the inside the receiver itself, the levels are reduced, a little bit of negative feedback, and the carriers are brought out more evenly. The receiver in an OFDM system generally doesn't care about all the rest of this. Doesn't make any hill of beans difference. It's only concerned with the carriers that it needs to receive in order to pass its traffic. So that saves our bacon when it comes to the downlink. And the downlink, we can set the transmit power to achieve the range that we want, and away we go. Our issue here is strictly in the uplink. All right. So now we have another concept here that we have to take and look at just for a minute. It's called best serving sector. So on this map, you can see that I've got 4 sectors on this particular site. I have customer premise equipment subscriber modules that are scattered here, there, and everywhere. The dots represent the subscriber modules, of course, and our range here, this is a couple kilometers, this scale bar right here. So we're talking maybe 5 kilometers or something like that in some directions, maybe 1.5 into the northeast here, so on. In this, we have CPE that are close to the site, and we have CPE that are far away from the site. Mixed, typical broadband arrangement where I'm trying to cover all of these, and I'm trying to do the best job where a subscriber out here has the same service experience as number 79 has here, right? So number 1293 and number 79 should have the same experience in my network. In order to accomplish this, we have to connect these CPE to what is known as the best serving sector. There's some things that happen when we're connected to the best serving sector that are very desirable, and there are some things that happen when they're not connected to the best serving sector that are not very desirable. All right, so in a typical sector here, I zoom in on our northwest sector here, our light blue sector, and you can see I've got a number of potential subscribers or some number of subscriber units that are in here that are meant to be connected to that northwest sector. What this map is telling us is that the best signal, the best RSSI, and therefore the lowest automatic transmit power control will be when number 79 is connected to, for example, this northwest sector, or 866 or 1665. They're connected to this northwest sector. What happens is the question. What happens if number 608 connects to this southwest sector? What's it going to experience? Well, in our little world here, since we're only a kilometer or two away from this, the signal strengths are going to be very, very high. So on the best serving sector, we might have a signal level of, say, -50. Let's say we take our number 866 out here, and on our best serving sector, it's got a signal level of -50 dB RSSI. Oops, make my M so you can read it. There we go, RSSI. Now, what happens if 866 here connects to the southwest sector? So I kind of got a polar chart that I laid down here, and I look at the angle, the difference in the azimuth between the best serving sector, which is the blue ray, and the adjacent sector, which is the red ray. So here on the blue ray, he's almost on the bore site. So if my signal level is -50 right here, then over here, since I am now 5, 10, 15, 20 dB off of that, I would expect that signal level to be -70. Can he connect at -70 and work perfectly fine? Sure can. -70 is not so bad at all. And so he could connect to the wrong sector and stay there. What else happens in here? Well, all right. So if this -50 here is generating a let's say a 35 dB signal to noise ratio, just for kicks and giggles here, just a 35. So at that point, I would expect that my transmit power at that point should be down at least that 35 dB or so from the maximum power of the CPE. So I have, if I take max power, let me write here somewhere here. So if I take max power of the SM, max SM, and then I would subtract my SNR, and that should equal the expected TX power. All right, so in this particular case, if this transmit power were say a -10 dBm, let's say in this case I'm transmitting at -10, signal's high, it's very close. Here, because I'm 20 dB difference in that, I would expect this signal to be 20 dB difference, so it's going to be at a +10. B. I almost failed grade 1 for obvious reasons here. My printing is atrocious. Anyways, so that's the difference between these two connections. If I connect to the best serving sector, I expect I would have a particular transmit power. If I connect to an adjacent sector or the wrong site, which is this is the worst case, a wrong site, maybe some value in between this, I would expect the transmit power of my CPE to be that much more in order to overcome this loss that the base station antenna is actually causing by being at the wrong azimuth. What does that do to my OFDM? Well, if I have this CPE that's screaming in order to take and connect to the wrong sector, his azimuth is still going to be pointed, of course, at the site. So therefore, this CPE is going to be received by the blue sector. It's going to be received, of course, on the red, which it's connected to, and it's generating a transmit power signal. The red connection here, this sector, the southwest sector, is telling it the CPE, the SM, to transmit at a very specific level, and in order to look like all of his CPE that are in the green sector here, because in fact that's what we're saying, is that this is in fact a green sector, but it's in the middle of the blue. So we have some problems that result. All right. So the next question is this: if the CPE is not connected to the base station, the best serving sector, I should say, what effects does that have on our system? Okay, so first of all, we have a problem that's called adjacent channel interference. Now typically the northwest sector here on a site, the northwest and the southeast are the same frequency, and then the northeast and the southwest are the same frequency. So let's call this F1, F2, F1, F2, in a case of reuse 2. So we have our 608 here that's on F2, transmitting 20 dB higher than the CPE all around it that are connected to F1, and so this energy, this extra 20 dB of energy, is going to have some effect on the noise floor here on F1. It's going to, since that CPE is in fact pointed this way, is going to take and raise the noise floor by some value. This raising the noise floor is called adjacent channel interference. So inside a channel, a typical broadband channel, we have a number of bandwidths that we have to account for. We have our definition of the channel by the manufacturer equipment, or by the FCC or Industry Canada, or whoever the regulating body is. It says the channel's got to be this wide. The manufacturer of the equipment, in order to pass the traffic that he needs, the necessary bandwidth is what's important. So on a 20 megahertz channel, this might be, let's say, 18 megs. So let's say this is 20 megs. This is 18. This is megahertz. And our occupied bandwidth might be 19 megahertz occupied, meaning that we've got 500 kilohertz of guard band on either side of this. And what's the definition of occupied bandwidth? The definition of occupied bandwidth is when the carrier the transmitter rolls off a certain amount of power. So the curve, the transmitters are never straight sided skirts. There's always roll off here. There's always energy that's bleeding outside of the channel in every case of every transmitter. No transmitter is absolutely perfect. We could never afford the filters that we'd need to be able to make it perfect. So transmitters would be hundreds of thousands of dollars if we had perfect skirts on them. So we don't do that. We have this compromise. So we're going to transmit a necessary bandwidth. We are going to occupy a particular bandwidth, and our channel is going to be a certain width. And then outside of that, this is called out-of-band emission. The out-of-band emission, in order for equipment to be certified by Industry Canada or the FCC, has to be below a certain limit. And there's a formula for that, depending on the band, depending on the equipment. So, but we have energy out there. We also have energy that's called spurious energy that's outside of the out-of-band emission, that's caused by a frequency in here, say maybe a frequency here, a frequency here. There's some frequency selective fading that goes on in here, and the result of this, if you know anything about intermodulation theory, F1 plus F2 equals F3. So depending on where this is, makes where that spurious energy happens to fall. If the whole channel is being spurious, then of course what happens here is that this bandwidth looks like that instead. If the channel is only frequency selective spurious, then we have energy that's outside of the channel, that's in very, very select areas of which we can mathematically calculate. Now, take this, erase this off, because I want to make another point here with this plot. Okay. So this is, if this is F1, then F2 looks just like this, except that it's going to be over one way or the other from F1. So if our channel bandwidth is 20 megahertz and our occupied is 19, headset's going to drive me crazy here. If our channel bandwidth is 20, then our next channel out here, let me get rid of my out of band emission. My next channel is going to be 20 megahertz out here. And it's going to look exactly the same as this 20 megahertz. If I have equipment in this channel, then my necessary bandwidth is going to be exactly the same, maybe 18 megahertz. Maybe my occupied bandwidth is going to be exactly the same at 19 megahertz, and then my channel at 20. So interesting thing here. Look at if I am generating spurious inside of F1, if this is F1 and this is F2, if I'm generating spurious in F1, look where it shows up. It shows up in the middle of F2. So what's it doing in this case? It's raising my noise floor here. It's making it harder for my receivers on F2 because of the fact that this energy is here. If this energy, if it were spurious right across the band, look at this. So in this case, then my noise floor is being raised on over half of my F2 channel because of transmitters on F1. How about that? So in a typical broadband receiver now, this is all part of the design. I have in a receiver, I have a certain amount of what's called adjacent channel rejection. So when I have a receiver that's operating here in F2, I'm protected from energy in F1 by some values. The typical values right here. So when your channels are immediately adjacent to each other, you typically have about 28 dB of protection. When the channels are 2 channels over, that increases to about 42 dB. And the maximum of a broadband receiver of any kind is about 48 dB. So that's max. So in this case, if I had 3 gigahertz co-located with 5 gigahertz, and my 3 gigahertz is screaming, my 5 gigahertz is offering 48 dB of protection from that screaming 3 gigahertz signal. If I am if this was let's say 5500, just for numbers, if F1 were 5500, excuse me here, 5500 megahertz, and F2 was 5520 megahertz, then the receivers on F2 are going to offer about 28 dB of protection from F1. If they were 5540, if they were one more channel over, I would have about 42 or dB-ish of protection from F1. So in the ideal channel plan, it would be really great to use every other channel from a broadband equipment perspective, but that's not possible. Like in the 3650, for example, here in Canada and what used to be in the US, you only have 50 megahertz of spectrum. And if you're using a 20 megahertz channel, that means the most you can separate them by is 10 megahertz. But so we're going to be somewhere in between this 28 and 42. And if you put the channels right against each other, which is the efficient thing to do, and that's what GPS synchronizing allows you to do, then you're going to have this 28 dB of protection. So I got to maximize this 28 dB of protection. How do I do that? If I'm connected to my best serving sector, my transmit power from my CPE is as low as it can go. Then the base station right beside, for example, in the uplink, in our case, oops, oops. All right, let me erase this. All right. So in our case here of F1, F2, F1, F2, if 608 here is transmitting at its proper -10, then I actually have protection here on my adjacent sector by 20 dB plus 28 dB for my filter in my receiver. So that means that that my neg, if I'm at neg 50 or neg 60 is my target level here on the northwest sector, the energy that the southwest sector will receive is going to be 28 and 20 dB of the antenna difference in gain different. So it's going to be 48 dB lower. So if this is -60, this is going to be, if the northwest sector is -60, then the southwest sector for the 608 is going to be -108. But way below the thermal noise floor. Doesn't cause a problem. It's okay. Let's go the other way now. Let's take a look at 608 connected to the wrong sector. Now he's going to be transmitting 20 dB higher than that. So he's actually going to be received at -40 here on the northwest sector, even though he's transmitting here. Then the sector's got 28 dB of protection. So that's only 40 minus 28 is -68. So now he is increasing the noise floor by about 20 dB. That's our problem. So if this noise floor is increased by 20 dB, then what happens here? The base station then tells all of these CPE to turn up the power by that same amount of the noise floor. Then everybody's talking loud here. And the actual CPE that are connected to F2 here then have a bigger problem because there's all this energy is being received all over. So all that we've done is we've increased the noise floor on the tower. Now this happens big time in 5 gigahertz especially when you have systems that are not synchronized. When you have systems that do not have GPS sync, this problem is actually exacerbated even more because I could have a situation where F1 is in receive and F2 is transmitting at the same time, and then I've got this noise that's coming from the system all added to this together, and it makes for a very chaotic and almost unmeasurable environment, except that you see crappy data rate. And that's why with lots of systems, you can put 10 or 15 or 20 subscriber modules on a sector, but you can't go any more than that because now we end up with a problem of this noise floor coming up too much. So you've got to add another access point. You add another access point, and you've increased the noise floor again by a certain amount. And so this problem is cascading. I call it the spiral of death for a broadband system, is that we need to be able to serve our customers with as few sectors as possible in order to take and make sure that the noise floor stays reasonable, and we can take and pass the traffic that we want to pass. In our case here, we end up in a situation where that's not the case. We're going to be finished here because of this adjacent channel interference. Oops. Okay. All right. Clear as mud? I hope so. Because some days it's not for me, but I try. And when we do radio network plans, we take all this into account. So what are some of the gotchas that you got here? So We've been through the math here. I can go through it again if you want. Send us a note at marketing at mbsiwave.com, and I'll be happy to go over this for you again. So, the conclusion. Each CPE receives all subcarriers transmitted at a constant downlink power. Each sector receives many CPE transmitting on a few subcarriers, but at the same time. Automatic transmit power control is necessary for maximum uplink performance on any system where we have multiple CPE transmitting at the same time. If you have one CPE transmitting at one time, the problem is not so bad on the same sector, but it is on the adjacent sector. It's no different. On the same sector now, because of intercarrier or subcarrier interference, we need to have automatic transmit power control to reduce the strong CPE to the point where they look like the same as the weaker CPE. Connecting your CPE and locking them there to the best serving sector is absolutely necessary for maximum data capacity. You shoot yourself in the foot if you just allow your CPE to connect to whomever they can find first to connect to. You need to lock them down onto the best serving sector. And every manufacturer of every bit of broadband equipment has a way of doing this somehow. You need to plan that. You need to take and make sure that the CPE connect to the best serving sector. The other thing that you do not want to do on a healthy broadband network is allow the CPE to roam. You don't want them to be able to pick the sector that they think they should connect to, because it might destroy your data capacity of your entire tower because of the fact that you've got CPE that are connected to the wrong sector and are perfectly happy to stay there. So, and as a rule, the CPE should not be connected to any sector. This is real important. CPE should not be connected to any sector when the CPE must transmit at maximum to reach the target signal quality. So what does that lead to? Well, that leads to a threshold. You need to take and make sure that you have an installation threshold. If this threshold is not high enough, then you could have situations where CPE are transmitting at full power, and a full power CPE out in the field probably isn't healthy for the data throughput or the data capacity of your sector or even your tower site. So pick a threshold. In LTE, I tell people that the threshold should be neg 108 or neg 105 RSRP, the signal strength of an LTE resource block. In a 450 system, that number should probably be around minus 65 or minus 70 at the worst, but 65 or 60 is the right number. If you want a high capacity broadband network, minus 60 dBm RSSI should be the target of your network. Now, of course, in every sector, you're going to have somebody who's going to be a little bit lower. You can have one or two that are lower. You should not have a whole sector full of CPE that are all screaming at the top of their lungs in order to be heard by the base station. So that leads to high performance, and it is good network design to have all of your equipment on the sector running at as low a power as you can take to make your service work. So the business plan and the transmit power and your site selection and your CPE lockdown are all really important to the health of your network. So that's my little tech talk for today. If you've got questions, send them to marketing@mbsiwave.com, and we'll answer your questions. If you've got suggestions for topics, please send them. If you've got any comments at all, feel free to make them at marketing@mbsiwave.com, and we'll be happy to respond to you.
Amazing. Thank you so much, Dave. And I see that the next Tech Talk is going to be December 16th.
Fantastic.
Just in time for Christmas. Do you know what your topic will be yet?
I'm going to continue on with a little bit of quality of service and link budget and how the two are mixed together. So when you're thinking about setting that maximum information rate in your CPE, what does that mean? I'm going to broach that subject.
Amazing. Thank you. Well, thank you all, and look forward to the next one, Dave.
All right. Have a good
Have a
day,
great
everyone.
day. Bye.